Hi there. Welcome back to Weather Analysis with Mr. CB. So, I'm sorry if you've been following along. You might have noticed that it's been a while since I've made a video, like a couple weeks. Sorry about that. I actually got pretty sick for over a week, and I don't know if I had COVID or what it was, but I was not in a position to make videos at that time. Um, But we're back, so let's continue with what we were talking about before. Or actually, no, we weren't talking about this before. Sorry. I think I made one of these videos, but I'm just remaking it now, so never mind. Okay, so let's talk about a radiosonde. So, what is this? Well, as you may know, the National Weather Service offices happen to release two weather balloons each day. Now, that's actually not completely true because we do have some federal funding differences. So not all offices do that at this time, but in a normal situation, they would. And so the weather balloon, it's not just a balloon. I mean, obviously it has something attached to it. And what that is a radiosonde. So you can see in this picture, this guy has that thing right there. And this thing, they've tried to make it smaller, smaller and smaller over the years to reduce the environmental impact that that has when it goes down on the ground somewhere. It can go into a completely different state depending on what the upper level patterns might be. We'll talk about that later, but you never know where this is going to end up exactly, and we don't want just some environmental litter. So they've tried to make this smaller and smaller, but regardless, this is what we use uh, to collect the data that is presented on the SKU log P that we're going to talk about very shortly. And what that happens to be that it records is pressure, temperature, relative humidity, and relative humidity. Since we also know the temperature, those two combined help us know the dew point. So it doesn't detect dew point on its own, but you can calculate dew point from the relative humidity and temperature. Review the last lesson if you don't remember how that is. It also can detect wind speed and wind direction. The longes are at 0Z and 12Z. And if you remember, that is the Greenwich time, but unfortunately, due to the time, daylight savings, it's actually going to be different depending on the time of year of how you would calculate that. So right now, when I'm recording this, it's in September. So we would say that we're going to do -4 hours of what the 0Z is. So if we have a zero Z, then 4 hours before that, we're gonna have a launch at 8 a.m. That's gonna be the morning one. And then for the evening one, that's going to be 8 p.m. because these are 12 hours apart. But that's not the same once it's day or March, November to March. I sometimes get mixed up of which is daylight savings and which isn't, but it doesn't really matter for our purposes. Okay, so here is a map of the National Weather Service offices. You can see, as I mentioned, typically in a normal situation, all of these blue dots will all release these weather balloons 2 times a day. But the thing is, there can be some things that don't allow for that to happen, like if there's severe weather or some sort of notice from the head office. There can be different reasons why they might not do it. That doesn't really, that's not really something you have to know though right now. So, and like I said, for federal funding, we have a not having an opinion either way uh stated in this video, but we do have a current administration that is stripped some funding. So unfortunately, not all those locations right now are able to launch both balloons. But anyways, like I said, the data that these weather balloons, the radiosonde on it, will be able to detect is going to be displayed on the QT log P. But before we talk about that, we need to think about these lines. Right now, there's no data on this. These lines that are here are going to be just what it always is. So they're constant. These are just environmentally expected values for these different things. We're going to talk about exactly what they are. So on the left here, that's pressure. And yes, it makes sense that as you increase with height, pressure goes down. We know that, right? But if you see the numbers of these are not exactly spaced evenly. They are closer together to start and further apart as you go up. And that means that it's actually a logarithmic um, relationship between uh, height and pressure and height. And so that is exactly why they call it log P. That's where that part comes from. Now we also have temperature lines, but the temperature lines don't go straight up and down. They are skewed, so that's how we have skew T. Now, there are different reasons for this. It's not just for no reason, but this is the best way to represent this data without it making the other lines would have to be tilted. Um, that's not really something you have to know, but the temperature lines are skewed. Now, something that's going to be important for that is when you're thinking about what is cooler and warmer, you'll have to make sure that you maybe tilt the paper you're looking at or just think about it that way. Like, if we go from, you know, here to here, that's actually not much of a temperature change, but from here to here, it's bigger. So you have to think about if it's perpendicular to that line or not. Um, then we also, so I should have said that those lines are solid and they're running like that from the bottom left to the top right. Now we all have other lines that are running from the bottom left to the top right, but they're dotted. And that's the saturation mixing ratio. We talked about this some before, but this is representing the capacity for water vapor. And it is grams of water that's needed to saturate 1 kilogram of dry air. Now, one thing that's going to be useful um, for these lines, or what they'll be useful for, I should say. We're going to talk more about this later. I don't remember if it's in this slideshow. I think it's the next lesson. But once we get that data from the radiosonde, we can do what's called a parcel trace, which is basically saying what would a parcel of air do as it goes up. And what that trace can then do is tell us things like K%, which will help us well, in the case of Cape, determine possibility of storms. So that's the reason. And that parcel trace that we do is based off of these lines. So that's the reason why they're there and why we might use them for something. Now, there are other lines that run the other direction from the top left to the bottom right. There are solid and dashed lines in that case too. The solid ones that are going that way are the dry adiabats. And basically what that means is it's just telling us basically the rate of temperature change as a dry parcel of air rises. So if the parcel is dry, this is how temperature is going to change. And this is roughly 10 degrees Celsius per kilometer. You can see in relation to the temperature lines, that is what this line is doing. It's roughly 10 degrees Celsius per kilometer. We're going to consider that constant. Technically, in the real world, just like so many things, it's not going to be exactly 10, but we're just going to say that it is for our calculations and purposes right now. So this line, it's not perfect, but we're going to just say that it's roughly 10 degrees Celsius decrease in terms of temperature. So if the temperature line's right here, that's what we'd expect per kilometer. Now, there's also dashed lines, um, and the dashed lines are going to be our wet adiabats. That means, okay, well, once the parcel is saturated, this now is what it will do as it goes up. This is the temperature change. And that is roughly 4 to 7 degrees Celsius per kilometer. So any of these adiabats are just saying, here is how temperature is going to change with height. Now, it depends on if the parcel is saturated or not. Not saturated, we use this one. If it is, we use this one. If it is saturated. And for us, we're going to use 6 degrees Celsius. That's the rough estimate that we'll use for this. I should have put that on this slide. It's really 4 to 7, but we'll just say 6. So once again, this is how temperature is going to change with height if the parcel is saturated. Um, all right. Once saturation happens, the dew point temperature is actually going to decrease at the same rate as temperature. And we'll have an example of that later on. All right, there we go. So now those are the different things. So we have 5 things basically. We have pressure, temperature, saturating mixing ratio, wet and dry adiabats. Now all that data is in all those lines are just in the background. The radiosonde is going to produce what we see here, which is going to be the green and red lines. That's the most important for us. The green is dew point temperature. The red is environmental temperature. So now let's talk about 3 different types of atmospheres. These atmospheres, um, looking at the skew T log P, we are able to know which type of atmosphere we might have. We could have a stable atmosphere. A stable atmosphere is going to have warmer air above cooler air. And the parcel, you have to think about it. If there's a parcel within that, if it has a lower temperature, it's going to sink. So any parcel that has a lower temperature than its surroundings will sink. Any parcel that has a higher temperature than its surroundings will rise. So basically what happens is since you have warmer air above cooler air, the parcel that's right here, it's going to be cooler than its surroundings, so it's going to sink. One here is warmer than its surroundings, so it's going to rise. They meet in the middle, as you can see by those arrows, and that means that there's equilibrium created, which is why it's considered stable. Unstable is reverse. Now we have cooler air above warmer air. So that parcel that's in the cooler air is warmer than its surroundings, so it wants to rise. Parcel that's in the warmer air is cooler than its surroundings, so it wants to sink. So that separates there. Um, and because of that, there's going to be instability. And we can actually have some vertical development of clouds because we're like, all these parcels are freaking rising right there. So, A, that's what's going to happen. Now, neutral atmosphere is not really as common, but that's going to just be if there's uniform temperature throughout. So there's not going to really be any movement at all. All right. Now we'll talk about the lapse rates. I pretty much already talked about this, but there are 3 types of lapse rates that we're going to talk about, and the lapse rates are just saying how temperature is changing with height. The environmental lapse rate, how do you calculate it? Don't have to. Um, Radiosonde does this. So that's going to be the red line. That's the ELR. The Dowler and Weller, that's the dry adiabatic lapse rate and wet adiabatic lapse rate. Also sometimes said as moist adiabatic lapse rate. But the dry one is always about 10. Remember I said that. 10 degrees Celsius per kilometer. So if the parcel is dry, we'd expect it to decrease by 10 degrees Celsius each kilometer that you go up. The wet adiabatic lapse rate instead will only decrease by 6, not 10. So that means that once the parcel is saturated, and we'll look at in the next video about how to know when that would be. But once it is, now it's only going to decrease by 6 degrees um, per kilometer. Um, all right. So that's actually going to be the end of this video. We're going to talk about um, how to look at this QT log P with this stuff in the next video. Thanks for watching.